Hello, students. Have you ever wondered why copper wires conduct electricity so efficiently, why glass simply blocks the flow, or why some materials behave mysteriously in magnetic fields? That's the fascinating world of the properties of solids. Solids are not just rigid substances, they come alive with unique electrical, magnetic, and dielectric behaviors, all determined by the arrangement of their particles. Some solids are excellent conductors, others are insulators, and many lie in between as semiconductors. Beyond this, certain crystals can even generate electricity when pressed or heated. Today, let's unfold these properties and connect them to the materials around us, from smartphones and solar panels to data storage devices.
When we talk about electrical behavior, solids fall into three broad categories: conductors, semiconductors, and insulators. Conductors like copper and silver have mobile electrons that flow freely, giving them high conductivity. Insulators like glass and rubber have tightly bound electrons, so electricity can hardly pass through. Semiconductors, such as silicon and germanium, are special. Their conductivity lies between metals and insulators and increases with temperature. This can be beautifully explained using band theory. In conductors, the valence band and conduction band overlap. In insulators, a large gap separates them. And in semiconductors, the gap is small enough that heating promotes electrons into the conduction band, allowing current to flow. This principle underpins the entire electronics industry. Now, let's dive deeper into semiconductors. Pure silicon or germanium are called intrinsic semiconductors, and while their conductivity is modest at room temperature, it increases as electrons jump across the small band gap when heated. But the real magic comes with extrinsic semiconductors. By introducing controlled impurities, a process called doping, we can dramatically change their conductivity. Doping with pentavalent atoms like phosphorus provides extra electrons, creating what we call an N-type semiconductor. On the other hand, doping with trivalent atoms like boron leaves behind holes, giving us a P-type semiconductor. These engineered materials are the heart of transistors, diodes, and solar cells, the very building blocks of modern electronics. Solids also reveal fascinating magnetic behaviors. Diamagnetic substances like sodium chloride or titanium dioxide are weakly repelled by magnetic fields because they have only paired electrons. Paramagnetic substances such as copper ions or iron ions contain unpaired electrons and are weakly attracted. Then comes ferromagnetism, the strongest form, seen in iron, cobalt, and nickel, where electron spins align parallel, giving rise to permanent magnets. Antiferromagnetic materials like manganese oxide have opposite spins that cancel each other out, while ferromagnetic substances like FeO have unequal but opposing spins, resulting in partial magnetism. From fridge magnets to MRI machines, all of these behaviors are applied in our everyday lives. Next, let's look at dielectric properties. Dielectrics are insulating solids that become polarized in an electric field. They don't conduct electricity but instead store it by aligning their dipoles. Nonpolar dielectrics like nitrogen or oxygen can be polarized only when placed in a field, whereas polar dielectrics like water already possess permanent dipoles. When placed between the plates of a capacitor, dielectrics increase capacitance, making them indispensable in circuits, sensors, and communication systems. Imagine your radio, your TV, or even your smartphone. None of them would function without these dielectric materials quietly doing their job. Some solids showcase extraordinary effects. In piezoelectric crystals such as quartz, mechanical stress generates an electric current. This is why quartz is used in microphones and record players. In pyroelectric crystals, heating produces a small current. a property used in motion sensors. Then there are ferroelectric crystals like barium titanate, where dipoles align permanently but can switch direction when an electric field is applied. This is very similar to how ferromagnets behave, but with electric dipoles instead of spins. Finally, in antiferroelectric crystals like lead zirconate, dipoles alternate in opposite directions, cancelling each other. These unique behaviors are at the core of memory devices, sonar technology, and even ultrasound machines. So, let's quickly recap. Solids are not mere rigid substances, they come alive with fascinating electrical, magnetic, and dielectric properties. Band theory explains why some conduct electricity and others don't. Semiconductors form the backbone of electronics, magnets power countless technologies, and dielectrics store and control electric energy. Piezoelectric and ferroelectric materials go even further, turning stress or heat into signals and memory. Truly, chemistry at the solid state connects directly to the technology we use every single day. I hope this session gave you not just definitions and theories but also a glimpse of how these properties shape the modern world. Until next time, remember, every gadget you touch is chemistry in action.